A 4-bit model that's faster and higher scoring than an 8-bit model? That shouldn't be possible, but that's what I found. We've been using integer-based 4-bit quantizations for years. They're great, but last year, NVIDIA introduced a different kind of 4-bit. NVFP4, a floating point format, which I've covered on the channel before. So Julia, what about FP4?
If we take very large numbers and we compress them into 4 bits, we can keep enough precision so that LLMs work well enough.
So the question is, which 4-bit is better, integer or NVIDIA's floating point? And to test this, I reached for the mother of all open weights LLMs, Kimi K2.5. Here's DHH on Twitter. Kimi K2.5 continues to be my daily driver for all the basic stuff where I don't need PhD level intelligence. I just need it done quickly. David, how's the quality? Extremely good. One of its main advantages. Here's Cursor AI founder Aman Sanger explaining that their new Composer 2 model is built on Kimi K2.5 from Moonshot AI as the top performing base model after they tested many options on Perplexity evals. Kimi K2.5 proved to be the strongest. Now, I already tested Kimi K2.5 on my Mac Studio cluster on the channel before, but Apple Silicon runs MLX, and MLX doesn't do NVFP4. For that, we need NVIDIA Blackwell GPUs and really big ones. So my friends at Cirruscale, not sponsored, they let me use their HGX server with 8 B200 GPUs. NVIDIA SMI. And each one is 1,000 watts with 184 gigabytes of VRAM. That should do it. And the nice thing is, this machine can run both our integer quants and NVFP4. So I can do a true apples to apples comparison. Same hardware, same model, same prompts, same everything except the quantization format. Both are 4-bit, both run the same Kimi K2.5 model. The only difference is how those 4 bits are stored. One uses floating point, the other uses integers. And by the way, Moonshot's official Kimi K2.5 repo on Hugging Face is int4, coming in at a hefty 595 gigabytes in size. For the NVFP4, I'm using Cirruscale's Kimi K2.5 NVFP4 quantization, which is 591 gigabytes. We'll start with speed. Now, of course, on this setup, I'm going to be using VLLM, professional high throughput level memory efficient inference server engine. Okay, I've shown it many times on the channel before, and it's fast. So that's going to be the server side running on the HGX with the 8 GPUs. And on the client side, I'm going to be using Llama Benchy. This is a great throughput benchmarking tool. And of course, I'm going to use the same settings for both machines. For those of you that are curious, this is my VLLM command, Moonshot AI Kimi K2.5, tensor parallel size 8, because we have 8 GPUs. It's going to spread the model across all of them. And I also like to enable tool calling. This way the model can be used remotely through some kind of coding agent. And I've shown that on the channel before. Here's my client side command. I actually tested concurrency 1, concurrency 4, and 32. That's how many requests are being thrown at it at the same time. And we'll review that in a moment. At concurrency 1, C equals 1, that's a single user talking to the model, kind of like chat. NVFP4 generates 133 tokens per second. Int4 does 105. So there's a 27% advantage for NVFP4. And I push it all the way up to 32 concurrent requests. That's like either 32 users at the same time or an agent with 32 sub-agents. Both models scale impressively, about 11 times total throughput. But NVFP4 keeps its lead the entire way. It peaks at about 2,200 tokens per second, whereas Int4 peaks at about 1,800 tokens per second. Now, the per request speed drops as you add users, and that's expected. They're sharing the GPU. But NVFP4 stays about 20% ahead at every concurrency level. So the advantage doesn't shrink under higher load. Same for bits, but NVFP4 is consistently 20 to 27% faster. Why? Well, here's why. NVFP4 quantizes both the weights and the activations to 4 bits, whereas Int4 only quantizes the weights. It keeps activations in full 16-bit. You can see the total data moving through the memory here. 8 bits versus 20 bits total. Int4 is pushing 2.5 times more data per operation. On modern GPUs, where memory bandwidth is the bottleneck, that's the difference. So NVFP4 is faster, but speeds mean nothing if the output is worse. Does quantizing activations too aggressively hurt quality? For quality, I ran 4 standard benchmarks. GSM 8K, 200 grade school math problems. Human eval, 164 coding problems where I actually execute the code and check if it passes. Well, I don't, but my agent does. You crazy? I'm not doing all that work. And this one, instruction following evaluation for LLMs, IF eval, 541 instruction following prompts that test whether the model can follow precise formatting rules. And of course, my favorite, needle in a haystack. I don't know why that's my favorite. Seems like it would hurt, actually, if you just jump into that haystack. That's where I hide a specific fact inside a long document and see if the model can find it. Here's what I got. Math. Basically tied. Retrieval, both perfect. But look at human eval and IF eval. Int 4 is actually ahead on both of them. 59% versus 54 on code, 68 versus 65 on instructions. At this point, I almost wrapped up the video. The story was clean. NVFP4 is faster, Int 4 is slightly better quality, right? Well, something wasn't quite right. Something bugged me about this. 54% on human eval for one of the best coding models in the world? That's way too low. So I dug into some raw data. 62 out of 164 problems were truncated. The model never finished writing the code. Not because it couldn't solve the problem, because it ran out of tokens thinking about it. See, kimi K2.5 is a reasoning model. Before it writes any code, it thinks internally in hidden tokens that count against your token budget. When max tokens is set to 2048, the model would spend 1800 tokens reasoning and have almost nothing left for actually writing the code. Sometimes it produced nothing at all, like an empty response. So I reran the benchmark with max tokens at 8,192, giving the model enough room to think and write code. And look at the difference. NVFP4 jumped from 54% to 88%. Int 4 jumped from 59 to 92%. Those are real numbers. The model was always this good. I just wasn't giving it enough room. And same thing happened with IF eval. NVFP4 had 185 truncated responses, 135 of them completely empty. When I reran with enough tokens, both models jumped up to 80%, and NVFP4 actually pulled slightly ahead. Looks like the Int 4 quality advantage was a measurement artifact. NVFP4 reasoning is more verbose. It thinks longer before answering, so it got truncated more often. And once I fixed that, they were essentially tied. And this is the trap that anyone benchmarking reasoning models can fall into. Standard token limits silently break your results. What ends up happening is the model that thinks harder looks worse, which is exactly backwards. So here's where NVFP4 and Int 4 actually stand with the corrected numbers. Quality, tied. Math tied, instructions tied, retrieval tied. Int 4 has a small 4% edge on code. That's it. Speed, not tied. NVFP4 is 27% faster, peaking at over 2200 tokens per second when we're doing the concurrency of 32. If I had to pick one, NVFP4. Same quality, meaningfully faster. But I wasn't done. I wanted to test one more thing. FP8 is an 8-bit floating point, twice the precision of NVFP4. In theory, it should be slower, but more accurate. I downloaded an FP8 version of kimi K2 base and ran the full suite of tests. Now, I did mess up a little bit because here's a little caveat. This FP8 model is actually the text-based only version of kimi K2. It's not a reasoning model. It doesn't have that internal thinking step, so keep that in mind. However, it's still interesting because the speed tests are still valid. If there was a kimi K2.5 in FP8, then this would be close to the result. And FP8 is the slowest, 96 tokens per second versus NVFP4's 133 tokens per second. That's 28% slower. More bits means more data moving through the memory bandwidth, and that's the bottleneck. But does the extra precision that we have with FP8 buy you more quality? And the quality story is not what I expected. Here's human eval. FP8 drops to 76%. The reasoning models are at 88 and 92%. Thinking before coding adds 12 to 17 percentage points? Who would have thought? This is where I realized, oh, wait a minute, FP8 is not a reasoning model. That's why. So I reorganized my chart labels a little bit to reflect that. But the interesting thing this shows is that on complex tasks, reasoning is a massive advantage. However, look at math. FP8 scores 97.5% here, higher than both reasoning models. It answers directly, without overthinking. Sometimes reasoning actually gets in the way, like with simple math problems. That's why the motto of this channel is probably going to be use the right tool for the right job. Now, instruction following, FP8 is at 64%, and kimi K2.5, the reasoning models are at 80%. Precise constraint following benefits enormously from step-by-step thinking. So, the FP8 results reveal something deeper than quantization. The biggest quality differentiator isn't the number of bits, it's whether the model can reason or not. Here's a chart that says it all. X-axis is speed and Y-axis is average quality. You want to be in the top right. NVFP4 is the closest. Int4 is a bit more accurate on code, but noticeably slower. FP8 is bottom left, slower and less accurate overall, despite having twice the precision. Now you might be wondering how you can actually run Kimi K2 yourself. Fair warning, it's a huge model. You're gonna need serious hardware, like a stack of Mac Studios, or a B200 cluster, or something along those lines. Or if you don't want to deal with the hardware, you can just use the official Kimi cloud provider and hit the API, or chat. Hi, I'm trying to stump it right now. Hello, how can I help you today? Didn't stump it. Thanks for watching. You probably will like this video next, and I'll see you next time.